pick a different point. How about, I don't know, n of, let's do 0, 0. That's lazy. What's that give us? If I plug in 0, 0, what do I get? 0. Uh-oh. Curses pi. Fine. Pi. Haha. Oh, no.
Try to get the tangent to be 1.
Pi over 2. Then I get what? Sorry, I'm 1, 0. Wait a minute. I did the same thing again, didn't I? Just a second. Let me reboot. Let's do this the other way around. What point can I put in here? So that this is where this breaks down. This is where, tangent z equals to y over x fails. Right. Okay, so let's see. How about if I put in the point, I want to put z equal to 0. 1, 1 pi over 4. That's what you want? That's what I want, though. 1, 1 pi over 4. Yeah, that's a point, right? That will solve this equation. What's the what would the corresponding? How would you get 1, 1 pi over 4 from the parameters, though?
U would have to be root 2, and V would be pi over 4.
Root 2 and pi over 4 would be, yeah, that's right. So square root of 2 times square root of 2 divided by square root of 2, and square root of 2 divided by square root of 2. So that give me 1, 1, and then pi over 4. Very good. Thank you. That's an interesting point. I like it. So here, not n, that would be r, right? What's n then at that point? What would the normal at square root of 2 come pi over 4 be? You got what? You got 1 over root 2 minus 1 over root 2 and root 2. There we go. All right, so there's our normal. There's our point. Let's see how it goes over here. We have the gradient of f at the point 1, 1 pi over 4. What do we get? Tangent pi over 4, right? Minus 1. X, which is 1, times this what? Secant squared, I'm just going to rewrite that as 1 over cosine, right? 1 over cosine squared of pi over 4, right? I don't know if you can recognize it or not, but this is 1 minus 1, and that's 2. Is that the same as this? Well, no. But are they pointing, are they actually just parallel?
Yeah, because that has
you multiply the whole thing by the square root of 2, then both are saying it's 2.
Right. I'm gonna take a slight twist on what you said. I'm gonna factor out 1 over the square root of 2 here, and I'm gonna say that then you can see that this one is just 1 over the square root of 2 times that one. So it's the same normal. It's just a question of rescaling, right? So the normal vector field, what you get from the cross product of the partials, doesn't have to match what you get from that, but they'll be the same. Well, they could be in different directions also, right? I solved for the level equation being x tangent z minus y, right? I could just as well have solved for y minus x tangent z, right? So the direction of the normal vector field is not significant unless there's further data. But as you can see, we get the same normal vector, right? And so then the equation to the plane would be what? It would be 1 times x minus 1 minus y times, minus, what was that? Minus 1 times y plus 1, y minus 1, plus 2 times z minus pi over 4 equal to 0. That's the equation to the tangent plane at the point in question we just worked out. Does that make sense? How does the graphical perspective compare with these two? I mean, which is easier, by the way? I think it's pretty obvious that if you have the equation as a level surface, it's way easier to calculate the gradient of the level function and plug in the point. The reason, though, we talk about the parametric viewpoint is this is what we need to do surface integrals towards the end of this course. All right? So this is a necessary calculation for us. It's not just some extra math thing I'm doing to be mean to you. I'm trying to prepare your mind for the surface integral we'll do later. So you have some sense of what a parameterization is and what a normal vector field is before we use them to calculate other things.
So is that why you're using the funny S thing for surface?
Yeah. Oh, just to have something generic for both. I mean, the reason I have the funny S thing is so that I can talk about it independent of the particular implementation, whether it's parametric or it's a level surface, it's S. Both are S. It's just different viewpoints for S. I could even look at S as a graph if I'm so foolish. This as a graph would be what? Z is equal to inverse tangent. Inverse tangent of y over x, right? So the so-called Munch patch R of xy, if you use x and y as parameters, which is really what you're doing with a graph, then the parameterization would be x comma y comma inverse tangent of y over x. That's another parameterization of this surface, which is essentially the graph. The graph is saying z is equal to inverse tangent of y over x, right? We'll say, no, graph's not a parameterization, it's an equation. It's z equals inverse tangent of y over x. I mean, I kind of agree with you. That's my point. The graph is the middle ground. It's kind of an equation, but it's also you can easily convert it to a parameterization, right? Where the parameters are x and y. All right. So I want to just take a second and do something a little bit general here. I want to try to work our way from an arbitrary graph to what's the normal vector field. So this is kind of a meta example I'm about to do, but I hope you can follow it. I think it's important to have this discussion at some point so that you can connect the viewpoints completely. And I might be wrong. Okay, so here's our starting point. Suppose z is equal to f of xy. All right. Some graph, right? So let's say xy in the domain of the function, all right? I want to figure out what's the normal vector field of that. There's two kind of ways I can go, right? What are the two ways I can go? I can convert it to a level function, right? What's the level function? You got two choices. Z minus f, right? Or f minus z. I'll do this. So then what's the normal vector field? Minus fx minus fy, 1. There you go. That's the normal vector field to the graph. How would we derive the same thing from the parametric viewpoint? So the parametric viewpoint says, well, the graph is really the parameterization, where you're using x and y as the parameters. And then the parameterization is just what? It's x, it's y, And then for z, you've got f of xy. So I can calculate partial r partial x. And I can calculate partial r partial y. And what will I get? One, 0, fx, yeah. And this one I get 0, 1, fy. What's the normal vector field then? The normal vector field at xy is partial r partial x crossed with partial r partial y. And so I got to take the cross product of these two vectors. So let's see, to get the x component, I do this minus that, so I get minus fx. The next one, I get minus fy. And then 1, yeah. I got lucky, right? What would have happened if I had ordered the parameters differently, by the way? What would the difference be? If I had said n of yx, that would be something else, right? Maybe I should call it n2. I don't know. That would have been partial r partial y cross partial r partial x, right? That would have been fx, fy minus 1. So which one's the right normal vector field to use to find tangent planes to a surface?
Yes.
Guess? Depends on the problem, depends on the context, right? Oh, yes. Oh, I thought you said guess. Both kind, I mean, not incorrect. I mean, whether you said yes or whether you said guess, I mean, it's 50-50, right? In 3 dimensions, there's just 2 normals to a surface. I mean, it's good. If we were in 4 dimensions, it would be harder. You have a whole plane of normal directions. That would be annoying. So let me just bring this back down to earth here for a second. Find equation of tangent plane at 1, 1, I don't know, I'll fill in the blank here in a second, of z is equal to, let's say, 6 minus x squared minus 2y squared. Apparently 3. And then I would say assume that the normal's pointing upward. Find an equation of the tangent plane at blah of this with upward pointing normal. What should that be taken to mean? We usually think of the z direction as being quote unquote upward. So which one of these is pointing up in the z direction? The first one, right? So yeah, so I mean basically we just by the previous work, you know, n equals the gradient of, well, z minus f of xy. Well, in this case, z minus 6 minus x squared minus 2y squared, following the previous example, right? Which is what? I mean, I could just use the previous example if I wanted. What do I get? I get 2x, 4y, 1. So the normal at the point 1, 1 is 2, 4, 1. And so thus with, you know, this, if this is my normal, right? And if my base point is 1, 1, 3, which is given, all right, then I can write the equation to the tangent plane as what? 2 times plus what comes next? 4, yeah. Yeah, then just 1 or z minus 3 equals 0. I don't know, sometimes I just like to clean it up. This is 2x plus 4y plus z is equal to 2, 4, 6, 9. 9, yeah. I hope you see by now, finding the equation to the tangent plane to a surface is not a hard problem, right? But I want you to understand the interplay between these different viewpoints because we use all of them, right? So it's important. Let me mix it up for just a second here. Throw in an example of a different sort. Nah, I won't do that. Let me not spoil a nice thing and start talking about, we'll talk about the curved linear coordinates another day. I'll just stop here while it's nice and pretty and go on to the next topic. Uh-oh. Before I do that, though. Oh, no! Oh, no. Oh. Well, I hope I wasn't going to project anything. It's out. Out of juice. I left it downstairs. Phooey. So you guys have any questions about anything before I go on here? Yes, sir.
Could you just explain why the gradient is normal?
Yeah, absolutely. I can do that. So the question really is, what is the normal vector field to start with? That begs the question, what is the tangent plane, right? So I say a natural viewpoint for what the tangent plane is it's the set of all tangent vectors to a given point. So if I think about some surface, right, whatever, and pick some point on the surface, let's say P, and I'm going to take the level surface viewpoint because it's the easiest one to discuss. So we have f of P equals to some constant c. This is the level C surface, all right? And I want to describe what's the tangent plane to that point P. So what I'm saying is that you can look at all curves on the surface, like a curve gamma, and that will have a tangent vector, right? And I can look at another curve, and that will have a tangent vector. And I can just keep doing this and doing this and doing this, and eventually all of those tangent vectors should fill out, you know, what we would call the tangent plane to the surface. Then the normal vector should be, well, the normal to that plane, right? So if that's n, we should have what? We should have that the normal vector is perpendicular to gamma prime of 0, assuming that gamma of 0 is P. So let's, think about curves that go through the point P and just set them up so that at time 0 they hit the point P. We can do that without loss of generality. Okay, so what does that have to do with the gradient? Right? I haven't said anything about the gradient. But let me tell you what it means. What does it mean for gamma to be a curve on the surface? What does it mean for that curve to be on the surface? It means that if you look at f of gamma of t, right, and I probably should put a vector on it because it's a space curve, right? It means that when I plug in the curve into the defining equation, the level equation for the surface, it should satisfy the equation of the level surface at each point along the path. You with me? So I can differentiate this. Differentiate with respect to time. Now what's the derivative of c? That's easy. Was that a bless you or a 0? You're not going to tell me, are you? All right, see if this can go better. I don't know. I threw one, like, it was sad. It was the worst. I mean, you just don't even know. Like, there was, oh, okay. Ah! I'm not sure. I don't think I'll be able to throw anything today. There's something wrong with the way I'm throwing. Oh, no. Statistics. Eventually I'll get it in. So the thing is, guys, this is, remember we proved the chain rule, whether you liked it or not? We spent 15 minutes started the other day, and we worked out that this is the gradient of the level function, evaluated at the inside function, here is the space curve t, dotted with the velocity of the curve. So that's equal to 0. What's that say? It says that the velocity to the curve is perpendicular to the gradient evaluated at that curve. But that has to be true for not just one curve, but all possible curves through the point, right? So that implies geometrically that the gradient of f at the point gamma of 0, which is p, right, is at least parallel to the normal. So since we don't really care, the normal, we can make the normal as long or as short as we want. We just use it as the normal. We're done. I mean, the normal vector field, how tall does the normal vector field have to be? Is it 3 units long, Is it 2 units long? I mean, I don't know. Who cares? At the moment, it can be as long or as short as you want. It's just because what are we doing? I erased it, but we always use ABC as the coefficients in an equation. We set equal to 0, right? So what does it matter if you multiply by 3? Or even minus 3 at the moment? You still get the same Cartesian equation. There will come a time later when we'll want to normalize the normal vector field to length 1 for reasons of measuring flux, but we're not there yet. Does that? So that is why, that's the significance of the gradient. Now, I did say this the other day, but I don't think you guys are ready for it the first time I said it, many of you. I hope now it makes sense. It's important. This lays the groundwork for something called the method of Lagrange multipliers, which we'll do before you know it. So our next problem is partial differentiation with Ciety conditions, or sometimes it's called constrained partial differentiation. Here, we suffer certain ambiguities. The basic problem with these kinds of problems is you don't always know what's dependent and what's independent. So here's a typical setup. Maybe I'm given that z is equal to x squared plus y squared. And I'm also given that w is equal to 2xz. And then question might be, calculate partial w, partial x. I'm being deliberately, I think, ambiguous here to start with, but let me just do it. So how would you do that? So it looks like I could just do this, right? So let's see, that would be what? 2z, right, plus 2x partial z partial x in principle, right? But if z is independent from x, then what do we get? yeah, we just get twice z. But what if z is not independent from x? What if z is not independent from x? I mean, is z independent from x? This doesn't seem to say that. Yeah, what's partial z partial x there? 2x, right? So which one's right? It depends. This is a good answer. Yes. How many equations do we have? 2. How many variables do we have? 4. That's right. So think of it this way. You start with this 4-dimensional backdrop. You have 4 free variables. I impose 2 equations. If those equations are independent, that means I'm left with something that's essentially 2-dimensional. All right? What that means is there will be 2 independent variables if we look at solutions to these equations. That means that the other 2 variables are dependent. And you see there's not just one choice of which is dependent and which is independent. Okay? So this first calculation, I assumed what? I assume that x and z are independent. If partial z partial x is equal to 0, that's part of what it means for x and z to be independent. All right? And so you'd like some notation which reflects this, because we don't want partial w partial x to be ambiguous. So what we typically do, what I do anyway, is I just put parentheses and then I put like a little sub z here. And that means that I'm differentiating with respect to x while I'm holding z fixed. In other words, that notation declares to the reader my independent variables are x and z. So as a sidebar, what are the dependent variables by process of elimination? Yeah, y and w. Now down here, what are my independent variables in my second thing? I assumed what? X and y are independent, right? Because here I took z to be a dependent variable. So this would actually be partial w partial x holding y fixed, which is a different rate of change than the other one. And so there's no contradiction. They're just different rates of change. This is not always emphasized in Calculus 3 books, and that's a shame, because many of you will want to take thermal physics, thermodynamics, right? And in that course, as you properly study it, you have to do partial differentiation of these equations, these so-called state equations. And there's lots of variables, and it's not always clear which one's a function of the other. So it's actually imperative that you figure out this issue of dependent versus independent so that you can make calculations logically. All right? Let me show you an application. So you guys have seen this before. PV equals nRT. This is what? Ideal gas law. Right. And we'll assume that R is constant. All right? Was that Boyle's constant or whatever? I forget. So let's see here. I want to show partial p, partial p, partial t, partial t, partial v, partial v, partial p is equal to something. Minus 1, in fact. Now, these three partials, if you write the same expression, if you write this one expression with these three partial derivatives, it's implicit that you've got your feet in both worlds. One of those partial derivatives says that t and v are independent variables. Another one of these partial derivatives suggests that v and p are independent variables. The third one actually suggests to me that p and t are independent variables. Let me make it more explicit. So to be more explicit, this really would be what's left over, v, p, and t. Depending on what you're reading, people may or may not actually bother to write what I just wrote in blue. Some people would argue, what else can it mean? I can't argue with them. I mean, it's true by process of elimination. It has to mean what I wrote because you've got one equation and three variables, right? That means there's one dependent and two independents, right? If you're starting with a three-dimensional context, you have one equation. That means it's a two-dimensional. There's two independent things left over by just counting. So what's partial t, partial? So let's actually calculate these. Partial p, partial t is what? Holding v fixed. I mean, you can solve, that's partial t holding v fixed of what? nRt divided by v, right? That's p. What does that give you? At minus nRt over v squared, right? What's partial p, partial t, partial v? Holding p fixed, what's that equal to? You can solve it, right? What's t equal to? PV divided by nr, right? Oh, I guess you could have complained I didn't say that n was constant. Oops. I mean, n is the number of moles. It doesn't have to be constant. This is the ideal gas law, right? What do we got here? Oh, how about just p over nr, right? That one was easier. What's partial v, partial p? V is nRt divided by p, right? So I get what? Minus nRt divided by what? P squared, right? So you take all these three together and you calculate, what do you get? Partial p, partial t at v, partial t, partial v holding p fixed, partial v, partial p holding t fixed, and that's what? Minus nRt divided by v squared, p divided by nr, and minus nRt divided by p squared. So what am I left with? You cancel some stuff. This cancels with that. And I feel like I should have more v's. Well, anyway, what do we get? Minus what? Minus nRt divided by, so the p and the p, so this will cancel with that. So I get minus nRt, oh, it looks like an nRt squared divided by v squared. Is that right? Oh, pv squared.
Wait, isn't it positive on top? Because we didn't cancel the negative on the
Oh, thank you. Yeah. Anyway, do you guys agree nRt squared divided by pv squared? I mean, I might have made a mistake. It's possible. What is PV equal to? Well, PV is nRT, right? I am pretty sure I have a mistake here. So P is equal to nRT divided by V. Differentiate. Oh, look, the first one. Come on, guys. Come on. Come on, guys. Don't let me get away with this. Look at this. Look at this. Look at that. Come on. You make me feel like I'm all alone up here. This is NR over V, right? Come on. Look, 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 look. Differentiation with respect to T. So this makes this NR over V. Let me undo my, sorry, I just ran out the board. Let's see here, P divided by NR minus nRT divided by P squared. Now what do we got? The NRs cancel, right? And you got what? You got minus nRT divided by what? PV. All right, I like that. That's minus 1. You guys with me? So more properly, what we're doing right now, it goes under the title of implicit differentiation of functions of several variables. All right. So these calculations are ultimately justified by something called the implicit function theorem, which I will sometimes prove in advanced calculus. I always share the intuition in advanced calculus. I may or may not actually share the proof, depending on the class, my energy level, other things. So I want to share with you guys something, the so-called method of differentials. So the method of differentials is it's one of my favorite things, and well, here's how it goes. Basically, this: if I have w, which is some function of say x1, x2, xn, right? And then what I write is I write dw is equal to partial f partial x1 dx1 plus partial f partial x2 dx2 plus plus partial f partial xn dxn. You're like, okay, but that's just the total differential, right? Yeah, okay. Granted. So I want to show you how to think about our first example today in terms of the method of total differentials. And then I'm going to show you how I think about the second example today in terms of total differentials. All right? In some sense, this is just a different way to repackage the calculation. But if you understand what I do here, it's very freeing. If you don't understand what I'm about to do, you'll be fine. You know? Someday, when you're old and lying in your bed. Sorry, I don't have the Braveheart speech quite memorized. If I did, it would be better. But here. W. 2xz. So the deal is this. You take the equations that you start with, right? And you just formally differentiate them. You take the total differential. This gives you a linearized equation for the differentials. So like this, the differential, this gives me dz equals to what? 2x dx plus 2y dy. This one gives me what? It gives me dw is equal to what? 2 z dx plus what? 2x dz, right? And so this is the linearized equation. It'll be linear in the differentials. There's no square of a differential. You just have dx, dy, dz, dw. And so here's the rule of the game. You solve for the differentials, which are the dependent variables. If you do that, the partial derivatives are just sitting there. So what I'm saying is, to calculate this partial w, partial x, holding z fixed, I should solve for my dependent variables are what? Dependent are, which ones are they? W and y, right. So I'm going to do that calculation, I'm going to solve these for dw and dy. Well, y is easy, right? dy is equal to 1 over 2y dz plus x over y, or excuse me, minus x over y dx. So I just solved the first equation for dy. I could do that. It's nice. It's pretty simple to do that, right? And then how about the second one? dw? dw is what? Looks like it's 2z dx, right? Plus, oh, wait a minute. Oh, cool. Oh, oh man, when I make up examples, they're usually nastier than they need to be. This is just right. This is truly wonderful. So here's the awesome thing. Once you've done this, you can immediately read off partial derivatives. Whatever's here, all right? This will be, well, let me just rewrite it symbolically. This will equal partial y, partial z, holding the other variable x fixed, dz, plus partial y, partial x, holding z fixed to dx. This will be partial w, partial x, holding z fixed, dx, plus partial w. I'm just writing in these weird order because it's what I have over here. Partial w, partial z, holding x fixed, dz. And you can actually think of it this way. Okay, so to calculate partial w, partial x, let's say holding z fixed, I set dz to 0. Right? So if I have, I mean, this is how I thought of it, at least as an undergraduate. I thought, okay, if I put dz equal to 0, then that gives me like dw dx is partial w, partial x holding z fixed in that case. But more pragmatically, you can just, all four of these partial derivatives are immediately you can read them just by comparison. I need colors. This is that. This is that. This right here is that derivative. And I'll make this one explode. Actually, I kind of made it into a cloud. Sorry. Although that seems more appropriate for today. But as you can see, that's what we calculated, right? Partial w, partial x holding z fixed was 2z, right? That's what we got. See it? Yep.
For the dy, it equals the 1 over 2y minus x over y, and then in the...
So yeah, partial y, partial x holding z fixed is minus x over y. Yeah. I can see that from just comparing this and that. Why is it negative? Because there's a negative here. Oh, why is that negative? It's because I subtracted that to the other side, and then I divided by 2y.
So when you're solving for the partial,
That was like a robot sneeze. That was amazing. I don't know who did that, but that was nice. I wish I had that on tape. Robots sneeze all the time. Anyway, go ahead, yes.
So when you're solving the differentials on the right, are they always added to each other? Because of the...
Well, the point is, you take the given equation, you differentiate it, and then you just solve for the differential you're interested. We could solve for this. To get these ones, what we'd have to solve for would be what? We would want dw is equal to stuff, and what's the dependent variables here? dz is equal to stuff, right? Z and w would be the dependent variables in the second calculation. So can I... See, that's annoying, because... Well, actually, that one's good, right? dz is what? It's 2x dx plus 2y dy, right? And then the dw is what? It's 2z dx plus 2x dz, right? Now that I'm not allowed. I have to convert that. I can do it by substitution, though. I just take this, right? And I plug it up in there, and this gives me so that gives me what? That gives me 2z plus 2x quantity squared dx plus 4xy dy, I think. And that, of course, is also what we got, right? This is partial w, partial x, holding y fixed, which is precisely what we calculated right here. Now, if you're uncomfortable with this, it's not the end of the world. You can still do things like I was doing at the start of this discussion. You can just differentiate. Remember that partial derivatives of independent variables are 0. And so you just differentiate, mind your business, do the chain rule, you get the answer. But the method of differentials is living. It's really living. Oh, let me show you, though. This one's slightly complicated. Let me show you an easier application of the method of differentials. Suppose we have a function, a level surface, right? So you might have f of x, y, z equals to a constant, right? If I was to take the differential of that, what would I get? I would get fx dx plus fy dy plus fz dz, right? I can either solve this for x, I can solve this for dy, I can solve this for dz, and that will show me different partial derivatives. So like solve this for dz, for example. dz is equal to what? Minus fx dx minus fy dy divided by what? F sub z, right? Or just to expand it out, this is minus fx over fz dx minus fy over fz dy. So if you accept my message for today, which is that these tell me what partial, this tells me what? This tells me partial z, partial x holding y fixed. And this one, what's partial z, partial y? Holding x fixed, it's just that. All right. What if we solve for dy? What would the significance of that be? let me just pick one. What's the significance of, for example, this coefficient right here? What's this tell me? Partial y. Oh, I'm an idiot. What's wrong here? Okay, so this is partial y, partial x, holding z fixed, and that's equal to minus fx over fy. There's one other differential we can solve for here. What is it? We can solve for dx, right? What's dx equal to? Minus fy over fx dy minus fz over fx dz. So we can read different parts. Let's pick one here. This one would be what? This would be like, that tells me what? That tells me that partial x partial z holding y fixed is equal to minus fz over fx. I mean, by now you probably see the pattern. You probably know what I should write here once I write down the variables, even without doing the calculation, if you picked up on the pattern. So, any questions about this before I? So check this out. Given f of x, y, z equals to a constant. Suppose x, y, and z are solutions to a level surface equation, right? Then partial x, partial y, partial x, partial, what is this? Oh, partial x. I started this wrong. Sorry, confused. I was supposed to put a z here. Sorry, partial z, partial x there is what? Of course, this has to do what? This has to do what? This has to do what? By process of elimination, this holds z fixed, this holds, and this holds. And those are what? Partial x, partial y. Holding z fixed is what? Do we have that somewhere in here? Yeah, this one. Minus fy over fx. This one would be minus fz over fy. And this is minus fx over fz. Look familiar? That's not an accident. This is a general fact about function of three variables set equal to a constant. If you take these staggered partial derivatives, it will work out to minus 1. It has absolutely nothing to do with the ideal gas law.
You can ready for the entire class, haven't you?
Hmm?
You can ready to reveal that the entire class.
Oh yes, this is just as I had planned before class, of course. That's actually not true. The more I plan for a class, the worse it is. My best lectures are the ones which I have absolutely no planning for. It's not the sort of thing I can put in my portfolio, right? Like, dear administrator, I really need to prepare less for my class. If I would just never prepare for my class, my lectures would be like the most awesome they could be. Just not something you can really sell to admit. I mean, ask your dad how that would go.